wonderful Leman landscapes, the lake, the mountains, the valley floor. How were they formed? If we look closer, the famous Rhone Glacier contributed by gouging the valley and depositing morainic deposits of alpine origin. Here is a sectional view. The current depth of Lake Geneva is 70 meters above sea level. But if we remove the moraines deposited by the big glaciations, we arrive at an extraordinary depth of 250 meters below sea level. This is the true Leman Basin. How would the glacier been able to gouge such a depression? To tear away this enormous quantity of rock and deposit it at the level of the present-day Geneva, which stands on solid bedrock, undisturbed by natural forces. There is no easy answer, but an explanation can be found elsewhere. To find the answer, it is necessary to go back in time and invoke Alfred Wegener's brilliant theories on continental drift. 250 million years ago, all the emerged lands of the planet were gathered into a unique continent, the Pangaea. 220 million years ago, this continent started to break and separate into two parts. Between the two parts, a sea called the Tethys Sea developed, and in time became greater and deeper. These vast movements of continental drift naturally disturbed all the surrounding land, and in particular the area where much later our Jura will emerge. Here the region is temporarily transformed into a series of maritime lagoons. The climate of this period is very hot, an average of 25 degrees centigrade, and it varies between aridity and humidity. It is a kind of Dead Sea, with rivers coming from Morvan and Massif Central, bringing to the bottom of the lagoons an accumulation of oversalted gypsums, which will be exploited for their salt in the future between the 15th and 18th centuries. These gypsums are very soft and malleable. They are called evaporites, and while sliding on this natural lubricant, the future Jura wrinkles as a tablecloth would on a smooth table. During this time, the Tethys Sea gets bigger and wider. It becomes an immense ocean with currents which influence the climate. At the same time, as the climate cools, vegetation develops on the shores. In the south of Europe, partially flooded by all these geological agitations, a local deepening grows bigger. It is called the Alpine Sea, and at the bottom of this sea settles sediment and fossils which will become the raw material of the pre-Alps. A little further north, in the zone of the future Jura, and topped by the soft evaporites, settles the harder sediments of clays, marls and limestones. They will petrify in time, becoming more resistant but remaining relatively malleable. 150 million years ago, North Africa began to separate from Europe, and Spain parted from France. As a result of these new drifts, a long sea grows bigger between the Paris Basin and the future Jura. It is called the Jurassic Sea. New calcareous sediments accumulate on the floor of the sea, completing layers already deposited above evaporites and constituting the future wavy layers of Jura. Suddenly, 65 million years ago, the situation changes completely. Africa begins to move northward, and like a jaw closing, the old Tethys Sea decreases and is transformed into what will become the Mediterranean Sea, whilst Spain and Italy are pushed away to the north until, 60 million years ago, Italy penetrated the deep Alpine Sea. 45 million years ago, it began to repel the enormous mass of petrified sediments deposited at the bottom of the Alpine Sea. These sediments accumulated on the edge of the continent, then slid heavily over the surface. Their movements caused more and more important wrinklings. They swamped the Jurassic Sea, which decreases and withdraws westwards. 23 million years ago, the considerable weight of this mass causes the collapse of the edge of the continent. A very long arm of the sea builds up from Marseille to Vienna and bypasses the mass of the Alps. The big continental rivers pass now into this arm of the sea, digging deep valleys. The valley of the upstream Rhone, the primitive Arve, and the future separation between the big and the small lakes, all of which can be seen to this day in the Alpine mass. At the bottom of this sea settles marine molasse, which is a very hard stone, a fruit of the erosion of the nearby Alps. Relieved of the weight of this erosion, the mass of pre-Alps and Alps tends to rise, as would a boat which is unloaded. But Italy continues its powerful push to the north, turning back the edge of the continent, which folds strongly, forming a frontal sea. The courses of rivers are changed, and they now flow northwards. Part of the traces left by these important episodes in geological history is hidden above the Alps and pre-Alps, which since this period moved northwards. In addition, the course of rivers did not change dramatically, as there were intervals of peneplain during which streams varied only locally. The big glaciations gouged all the landscape and still complicate the interpretation of the hydrological variations. It is therefore only an approximation based on a network of insufficient proof. The Rhone becomes a tributary of the Rhine and begins to accumulate unrefined sediments torn away from the slopes of the Alps. The floods of rivers and advance of pre-Alps spread the sediments northwards. It is the beginning of the vast transformation which will affect all French-speaking Switzerland. It begins in the first wrinkling caused by the approaching movement of the pre-Alps mass. The Mount Pelerin is raised and blocks the course of the Rhone, which is forced to pass temporarily by Pléiades and Châtel-Saint-Denis, where it deposits river sediments easy to identify today. At the top of the wrinkling, the uplift of Mount Pelerin increases and extends westwards. Once again, the Rhone is turned and passes into the region of Lausanne, where it merges with the very old course of the Arve, which at that time still crossed the Central Alps. Both rivers, contained by rising Jura, pass together northwards. Pre-Alps are now preceded by a zone of peneplain, in yellow on the image, a low relief plain formed by protracted erosion, which is covered by a molasse of very hard fresh water. Near Geneva, 5 or 6 million years ago, the future Mount Selive is pushed away eastwards and begins to rise, its weight forcing the small lake, which is showing in the first undulation of Jura, to sink. On the other hand, the uplifted zone of Mount Pelerin continues to get bigger and spreads westwards. Once again, the Rhone and the Arve are diverted and begin to carve the deep valley of the intended Venoge. Indeed, this valley seems far too spectacular for the modest river Venoge of today. More or less at the same time, 5 or 6 million years ago, a considerable event takes place. Coming from the ocean depths of the planet, the crystalline massifs of Mont Blanc and Aiguilles Rouges tear through the surface and emerge in the centre of the Alps. Rivers located in the south are now going to pass from now on in the direction of the plain of Po. The river Arve also makes this change in direction, and it leaves the old geographical depression in which it was contained. Near to its former mouth, it is replaced by the river Drance. On the north side of the Alpine Massif, the pre-Alps continue their push towards the northwest, naturally contributing to the stress wrinklings of Jura. The relatively stiff layers of limestone slide on the very mouldable evaporites deposited at the time of the Thetis Sea, and the region of the peneplain helps transmit the movement. The northward movement of the enormous mass of pre-Alps causes spectacular sinking in the formation of the south shore of Lake Geneva. It is especially from Thonon and eastwards that this sinking is important, and it decreases in the direction of Small Lake. The north bank of the lake is, on the contrary, brushed back by the movement of pre-Alps. As a result, the zones of Duillet, Trelex, La Côte, Saint-Livre, Le Mormont, and finally all the Jura is compressed and rises. On the south of the river Thiel, beyond Vierdon, the ground tends to rise. Of course, these upheavals of the relief of the region cause a complete transformation of the hydrography. Rivers diverted by heightened Jura mountains completely change their direction, now passing towards the southwest by the Small Lake and Geneva. The supply of water to the river Venoge, emptying into the Big Lake, is considerably reduced in volume and importance. It is time now to look at the big glaciations and the tracks that they have imprinted on the relief of the Leman region, as well as the erosions they have caused and the moraines they have deposited everywhere. The last two glaciations are the one of the Riss, dated 450,000 years ago, and that of the Würm, which ended 11,000 years ago. A big glaciation can be classed as enormous, and specialists have identified more than 20 such glaciations during geological time. From the summit of the Alps, the glacier of the Rhone spread to the Lyon region of France, being pushed down the Leman pit by the weight of the pre-Alps. The glacier left enormous amounts of moraine. How did it happen? Let us imagine an immense pyramid of ice, several thousand meters in height. Its enormous weight will tend to flatten the ground beneath it. If an uncompressible wall, such as the side of a mountain, prevents it from spreading out on one side, the pyramid will tend to pass by on the other side more quickly and further away, whilst affecting the side of the mountain, especially at the height at which the thaw occurs in the summer. If more ice is contained in a valley, it will pass by faster, further, and with more erosion. When it arrives on the plain at the exit of the mountain valley, the ice is going to spread out widely and almost stand still. At this time, erosion is almost non-existent, but ice in successive waves piles up, and ice thickness increases in a considerable way. This is what happened with the arrival of the ice on the Swiss land base and on the Leman pit, which had just been formed by the weight of the pre-Alps. Little by little, the thickness of ice in this region becomes enormous, more than 1,200 meters, the ice tightening its hold on the land and the lake base. Yet, as a good heat insulator, from a certain thickness, the ice is not affected by variances in the cold climate of the period. On the contrary, at the base of the glacier and under the influence of pressure and the geothermal temperature, miners know that the temperature increases with depth, The ice melts and the rocky fragments carried down from the mountain fall to the lake bottom, so filling it with moraine. But because of its immobility and the water which serves as a lubricant, the glacier cannot erode except perhaps for a few scratches on the leading edge and on the flanks. The head of the glacier spreads out slowly over the region, finally arriving at the end of the lake in the zone of the future Geneva, where it is increased by ice flow from the west side of the Alps. Together they forge downstream into the valley of the Rhone, where they again begin their erosion to dig the U-shaped valley which will be the Lyon region of France. Meanwhile, other ice flows spread behind Mount Tendre to Neuchâtel and even beyond. Then comes the thaw, and the glaciers leave the moraines we find in the landscape. After the next glaciation, in 120 or 130,000 years, we will find our Lake Leman is completely filled with moraine, and our very, very distant future descendants will be able to farm on the surface and dig into freshwater swimming pools. What is directly observable in the region is rather easily understandable. On the other hand, what is hidden under the overlapping of the alpine masses requires a creative vision. Thus, part of my vision is hypothetical. Another day maybe, very deep soundings or heavy geophysics will lead me to specify or even change my vision of things. Having said that, it is necessary to pay tribute to the great scholars who explored, observed, and thought about the history of the frontal zone of the Alpine mountains. Maurice Lugion, Lake Geneva, Arnold Mercier, Augustin Lombard, and many other people on a list too long to enumerate here. Altogether, they made this region one of the higher places in modern geology, and it is largely on their works that I based my short synthesis summarizing the very complex history of Lake Leman.